So what does it mean for a function to be continuous? So a function is continuous if you can draw it in one motion without picking up your pencil. So looking at these graphs on the bottom, we want to see if they're continuous or not. So in the first one, if we go to draw our lines, we have to draw our line, pick our pencil up, draw our line. So is this continuous? No, it is not. Okay, so for the second one, it looks like it's continuous because it's a straight line, but if you look closely, there's a little open circle, and technically you go to the circle, you jump over it, and you come out the other side since it's an open circle. So this is also not continuous. There are a couple types of discontinuity you can have. You basically have removable and you have non-removable. So for removable discontinuity, that is where you have a hole in your graph. So sometimes it's going to look like this, where you just have a hole. Sometimes you might have a dot above or below the hole or even on the hole, still making it discontinuous because there is some type of gap in the graph. There are three main types of non-removable discontinuity, and that would be a jump discontinuity, so it looks like a jump, an infinite, which is when you have a vertical asymptote and then your graph is going either towards infinity or negative infinity, or an oscillating function where it's oscillating back and forth and it gets real squiggly and you can't really see what it's doing. So when you have a real squiggly one like that, that is also a discontinuity. So in order to tell if a function is continuous or not at a certain number, the following must be true. So this is very important here. Okay, so the limit as x approaches a of f of x has to equal f of a. And these three things are the three things we have to test every time to see if it's true. If all three things are true, then the function is continuous at that number. So the first thing is that the function at the value has to be defined. So it has to exist, meaning that the a value is in the domain of f. Number two is that the limit of f of x as x approaches a has to exist. So the left and right limit must be the same, the limit must exist. And for number three, the value of the limit has to be equal to the value of the function defined at that point. So if they're equal, then the function is continuous. Okay, and that is very important. So all three things must be satisfied for the definition to hold. So in order to prove continuity with a function, we need to make sure that we are talking about limits. So you should never be talking about continuity and explaining how something is continuous without using limits. Okay, so let's look at this example. So here we have a graph of a function f, and we want to know at what numbers is f discontinuous and why. So what we're going to do right now is just make sure we understand these 3 points here. Okay, so using these 3 points, we're going to look at the graph again, and we're going to see what points are discontinuous and because of which of these 3 is the reason why it's discontinuous. So the first point of discontinuity we see on this graph as we're drawing it from left to right is that we have a hole at 1. So I'm just going to put a little 1 here. So the first discontinuity is when a is equal to 1. And why is that discontinuous? Well, looking at our 3 reasons again, okay, that is actually because f of a is not defined, right? It's not in the domain. So since there's a hole here, the function evaluated at 1 doesn't exist. So we'll say because f at 1 is not defined. So then we move on to our second point of discontinuity. And as we're going from the left, we go, and here we get a discontinuity at 3 because we have a jump discontinuity, and it goes back up there. So a equals 3 is a discontinuity. And based off of our 3 reasons, why is this a discontinuity? Well, in this case, the limit as x approaches 3 doesn't exist. The limit as x approaches 3 of f of x does not exist. All right, and the reason it does not exist is because the limit from both sides are not equal. As I come from the left-hand side to 3, it's going to be this negative value. As I come from the right-hand side to 3, it's going to be this positive value. So since the limits from both sides are not equal, the limit doesn't exist. And then the third discontinuity, again, so starting at 3 where we left off, and we're going to keep going. So here we have a hole at 5. So a equals 5 is a discontinuity. But if you notice, there is a closed circle where a is 5, but it's above where the graph is. Okay, so that means that it's discontinuous because the limit as x approaches 5 of f of x is not equal to f at 5. So that's part 3 from our 3 pieces that are important. Okay, so the limit does exist. The limit exists, it's whatever this y value is here, because the left and right limit are the same. The function is defined. Okay, it's got a closed circle at 5 somewhere, but the two values don't match. So since that is not equal, we say that it is discontinuous at 5. So let's look at an example. So we want to know, is the function f of x continuous at x equals 3? So we have to test the 3 different scenarios and see if they're all true. So the first scenario we're checking is, does f at the value exist? So f at 3. If I look at my graph, or my function, the second function that we're using here includes the 3. Right? X is less than or equal to 3. So since it's equal to 3, then f at 3 is 3. So f of 3 equals 3. It's defined. So check. The second thing I'm going to do is I'm going to check the limit. So the limit as x approaches 3 of f of x. So we want to see if the limit exists. So the first thing, in order to do that, we have to check the limit from both sides. So I'm going to check the limit as x approaches 3 from the left. So as I'm coming from the left-hand side, based off of these 3 functions I could be using, I'm going to use the one in the middle, right? Because the one in the middle is saying x is greater than or equal to 1 and less than or equal to 3. So if it's getting closer and closer and closer to 3 from the left-hand side, that's going to be this function. So that's going to be f of x, and we said we're using the middle function, so limit as x approaches 3 from the left of 3, and that's going to equal 3. So I'm going to check the other side too. So the limit as x approaches 3 from the right of f of x. So if I'm going to the right of f of x, I need values of x that are greater than 3. So we're going to use this bottom function here, this x. So it's going to be the limit as x approaches 3 from the right of x. And if I plug 3 in using direct substitution, this is going to equal 3. So since the left-hand limit and the right-hand limit are both equal to 3, then we can say that the limit as x approaches 3 of f of x is equal to 3. It does exist, and it's equal to 3 because the left and right were the same. Now the last thing I have to check is the limit as x approaches 3 of f of x equal to f of 3? Well, the limit is 3. F at 3 is 3. So since 3 equals 3, they're both the same. Check. So that's true. So since all 3 things were true, we can say, yes, f of x is continuous at x equals 3. So we want to make sure that we check all 3 scenarios. If all 3 are true, yes, it's continuous.